hello again. In this example you will learn how to solve for reactions in a multi-connected structure. We're going to be taking a look at this particular beam, which is connected with a couple of hinges, internal hinges, also known as moment releases, and we want to be able to solve for the reactions in it. But before we solve for any reactions, let's make sure on the statical determinacy of this beam, make sure that we can even solve for them. So based upon the support types, I'm just sketching in the reactions that would be present. But anytime we have internal hinges, we need to make cuts before we can get a correct determination on the determinacy. So if you make a cut at an internal hinge, there are two unknowns that are present there. So let me just avoid confusion by indicating that we have indeed cut that. We have a total number of unknown forces then to be 9. That's 5 external reactions and 4 internal forces after the cut. Since we made 2 cuts, we have 3 structural pieces, and the total number of equations of equilibrium we have is 3 equations per piece times the total of 3 pieces. That'll give us 9. So 9 is equal to 9, which means that we are statically determinate. And since our reactions are not all parallel and they aren't concurrent, we can conclude that the beam itself is stable. Now I want you to think about us looking at this prior to having made the cut, and the total number of unknown forces or unknown reactions is we've got 1, 1, and 3. So solving for reactions with the entire structure assembled together is not going to be possible. And yet we know that it's statically determinate, which means we should be able to solve for these. Well, when dealing with multi-connected members, what we want to do is we want to cut them apart at the hinges or the releases, whatever those are in the structure. In this case, moment releases at points C and D. We'll then sketch the free body diagrams based upon the unknowns. So RAY, RBY, we then have unknown internal forces VC and NC, which incidentally carry over on this side. What you're going to notice is that when I sketch my unknowns, I am sketching them assuming as if they are positive. So remember, an axial force is positive when it is pointed out from the surface. That means it's in tension. A shear force is considered positive when it causes clockwise rotation of the member. And so with that, there's the positive sign convention for VD. And now we've got the reactions, of course, over here, REY, REX, and moment about point E. Now the free body diagram is not totally complete yet. We've got all the unknown forces on it, but we want to take that distributed load. We want to resolve it into an equivalent point load. Well, that equivalent point load is going to act at the centroid of that distributed load there. And so since it acts over 12 feet, this will act over 6 feet, and the intensity of this is going to be 30 kips. The way I got that 30 kips is I took the intensity of the distributed load, 2.5 kips per foot, multiplied by 12 feet is equal to 30 kips. Okay, now I would be prepared to start using equilibrium to solve for these unknown forces. But I need you to take a close look at each of the free body diagrams and see what you would be capable of solving for in each of these. Now you could just start with segment ABC, write a set of equilibrium equations using a total of 3 equations, and you could solve, but you wouldn't be able to solve them uniquely. What I would suggest is that you scan and look for a segment where you could solve for many of the unknowns. So segment ABC has 3 vertical forces, and that means I have summation forces in the Y and I have some moments to help me solve for that. Well, that's only 2 equations, but 3 unknowns. But you look at in the X direction in C, that is only 1 unknown, so I really could start with that, or look at member CD. I've got 2 unknown vertical reactions, or vertical forces, and that then I have summation of forces in the y and summation of moments. I could solve for both of those. But I only have one summation of forces in the x direction, so I couldn't exclusively solve for NC and ND. Now, segment DE has a total of 5 unknowns, so that would really be a poor segment to start with. So I'm going to go ahead and start with the middle section, and I'm going to sum moments about point C. That'll solve for the shear at D. I'm then going to sum forces in the y. That will solve for VC. And then I will sum forces in the x. And you'll notice when I sum forces in the x that all I can get is a relative expression, not an explicit solution to what those are. Please note that we've got a negative here and a positive here. Whenever we're dealing with internal forces, we always let the signs communicate those internal forces. Let's go ahead and translate those over here. We know that VD, we said, was negative 15 kips, and VC was a positive 15 kips. And so we can get those translated over onto the other free body diagrams. And then we can proceed with the rest of our analysis. Now let's look at the left section with some moments about point A. We'll solve for RBY, then I'll sum forces in the y direction. That'll give me RAY, and when I sum forces in the x, that tells me that NC is equal to 0, which from our previous finding would then tell me that ND is equal to 0. Let's go ahead and get those sketched on here. So RBY is equal to that 24 kips. RAY was equal to the negative 9 kips. Remember what the negative means? It means that it's acting in the direction opposite of what we have assumed. NC is equal to 0. Whenever we report reactions, I really do like to have an interpretive arrow. So with that being positive, I know I assumed the correct direction. With this being negative, I know I assumed the wrong direction, so it really is going down instead of up. Let's finish this example out now by looking at the rightmost section. There's our 3 equilibrium equations solving for the 3 remaining unknowns that we have present there. And so what remains is to just go ahead and provide an interpretive arrow. So ME, we decided, was that negative 120 kip feet. And so since it was negative, we know it's actually going in the other direction. REY is positive, so it's going up. And we definitely don't need an interpretive arrow for REX because it is 0 and has no specific direction. Well, that concludes this example. And remember, it is always a beautiful day to study structures.